somewhere near the very edge of what we can see, there are 31 objects glowing with the light of 1 trillion suns each. And according to the standard rules of physics, objects that are extremely difficult to explain using conventional black hole formation models. We're not looking at them as they are today. We're looking at light that left them more than 13 billion years ago, when the universe itself was barely 5% of its current age, just 670 million years old. At that point in cosmic history, galaxies were still assembling out of raw gas. The first generations of stars had barely finished lighting up the darkness. And yet, sitting right there in that impossibly young universe are supermassive black holes already weighing hundreds of millions to billions of times the mass of our sun. There's a hard physical speed limit on how fast a black hole is allowed to grow. Every one of them appears to have grown far faster than standard models predict. This is the story of the most ancient quasars ever confirmed. What a new sky survey just found hiding at the edge of time. Why the numbers genuinely don't add up, and what astronomers think might be quietly rewriting the rulebook for how the universe's biggest monsters are actually born. That's not a coincidence. 31 confirmed objects, all breaking the same cosmic speed limit. If that number surprises you, hit like and subscribe. Big Data Vault covers stories like this the moment they break. Every impossible object needs someone who first proved it was possible at all, and quasars owe their entire existence as a known category of object to a single night in 1963. Astronomer Martin Schmidt, working at the Palomar Observatory in California, was staring at the spectrum of an unusual star-like radio source called 3C273. It looked on the surface like an ordinary star, faint, blue-white, unremarkable. But its spectral lines refused to match anything in the textbooks. Familiar patterns of light that should have identified known elements simply weren't lining up, no matter how Schmidt tried to interpret them. Then he noticed something. The unfamiliar pattern was actually a familiar one, hydrogen's well-known spectral signature, but shifted dramatically toward the red end of the spectrum, stretched by a redshift far larger than anything previously measured for anything that looked like a star. That shift meant only one thing: 3C273 wasn't a nearby star at all. It was hurtling away from us at a significant fraction of the speed of light, which meant it had to be almost unimaginably distant. And yet, it was bright enough to see clearly from Earth. That contradiction, small and star-like in appearance, but distant and luminous beyond anything a normal star could achieve, gave birth to an entirely new category of object: the quasar, short for quasi-stellar radio source. Astronomers quickly realized what quasars actually were. Not stars at all, but the blazing, overactive cores of distant galaxies, powered by supermassive black holes feeding on surrounding gas and dust so aggressively that the resulting light output could outshine every star in their host galaxy combined. It's worth pausing on how strange this must have felt at the time. In 1963, black holes themselves were still treated by most physicists as a mathematical curiosity rather than a real astronomical object. The very concept was barely a decade into being taken seriously. Yet here was direct observational proof that something unbelievably compact, unbelievably distant, and unbelievably bright existed in large numbers across the sky, all before anyone had a confirmed, direct image of an actual black hole to compare it to. Quasars, in a real sense, forced astronomers to take black holes seriously as physical objects years before the theoretical framework around them had fully matured. For decades afterward, finding quasars was slow, painstaking work, one unusual radio source at a time, one redshift measurement at a time, gradually building a catalog of the most extreme, most distant objects the universe had to offer. Each new record holder pushed the known edge of the observable universe a little further back, and with it, pushed back the earliest moment astronomers could directly witness a supermassive black hole already blazing away. That slow, one-at-a-time approach just changed completely. Instead of stumbling onto quasars individually, astronomers recently completed something closer to a census. A systematic, wide-scale survey of the earliest, most distant reaches of the observable universe, built specifically to catch objects exactly like this in bulk, rather than by accident. The shift from accidental discovery to systematic survey matters more than it might sound like it should. Every previous record holder quasar, going back to Schmidt's original 1963 discovery, was found essentially one at a time. A single unusual signal, followed up individually, confirmed painstakingly through years of dedicated observation. A dedicated wide-field survey flips that entirely, casting a net wide enough and deep enough to catch dozens of these extreme objects in a single coordinated pass, rather than waiting for astronomers to stumble onto them one at a time across separate decades of work. The instrument responsible is the European Space Agency's Euclid Space Telescope, and its wide survey has just delivered a haul that dwarfs anything found through the old one-at-a-time method. 31 confirmed ancient quasars, all dating to the universe's earliest chapters, identified in a single coordinated sweep of the sky. Euclid wasn't even built primarily to hunt quasars. Launched to study the large-scale structure of the universe and probe the nature of dark matter and dark energy, its wide survey is designed to map roughly a third of the entire sky in extraordinary detail, cataloging billions of galaxies along the way. Finding 31 of the earliest, most extreme quasars ever confirmed is, in a sense, a byproduct of simply mapping everything else thoroughly enough, which says something about how much is still waiting to be found once an instrument is finally wide and deep enough to catch it. 2 of them broke every previous record. Designated EUCLJ 1729, 02.75 plus 6, 4, 1018.1, and EUCLJ 1253, 08.55 plus 7054, 3, 2.3. These 2 quasars sit at redshifts of 7.69 and 7.77 respectively, the highest, most extreme redshifts ever confirmed for objects of this kind. Translated into cosmic history, we're seeing both of them exactly as they existed, roughly 670 million years after the Big Bang. For context, the universe today is about 13.8 billion years old. This is a snapshot from when it had barely gotten started. And these aren't faint, barely detectable smudges either. Despite existing in the universe's earliest infancy, these quasars blaze with the combined light of roughly 1 trillion suns, easily outshining every star in their host galaxies put together. Bright enough that Euclid could catch them from over 13 billion light-years away, in a systematic survey rather than by pure chance. Here's exactly why that shouldn't be possible, and it comes down to a genuine speed limit built into the physics of how black holes actually feed. A quasar is powered by a supermassive black hole consuming a surrounding disk of infalling gas and matter, called an accretion disk. As that matter spirals inward under gravity, friction heats it to extreme temperatures, and it glows brilliantly. That glow is the quasar's light. But here's the catch. Light itself exerts pressure. Push a black hole to feed too aggressively, and the sheer outward pressure of its own radiation starts shoving incoming gas away before it can fall in, throttling the growth rate. This natural cosmic speed limit on how fast any black hole can consume matter and grow is called the Eddington limit, and it applies to every black hole in the universe, regardless of size or age. It's named after British astrophysicist Arthur Eddington, who worked out the underlying balance of forces in the 1920s while studying how stars themselves managed to hold their own shape against the crushing pressure of their own gravity. The same basic physics of radiation pressure pushing back against inward falling or inward collapsing material turns out to govern how fast a black hole's accretion disk is allowed to feed it. It's not a soft guideline, it's a hard physical ceiling, baked into the same equations that describe why stars don't simply collapse in on themselves the moment they ignite. Run the numbers using standard assumptions. Black holes are thought to begin as light seeds, the collapsed remnants of the universe's very first generation of dying stars, typically somewhere between 10 and 100 solar masses at birth. Even feeding at the absolute maximum rate the Eddington limit allows, growing a light seed like that into a fully supermassive black hole, hundreds of millions to billions of times the mass of the Sun, is expected to take billions of years. These 31 quasars didn't have billions of years. They had, at most, 670 million. And several of them appear to have already reached that scale within that impossibly short window. Something about the standard growth story is missing a piece. It's worth understanding how astronomers actually convert a redshift measurement into an age like 670 million years. Redshift describes how much a distant object's light has been stretched by the expansion of space during its journey to us. The higher the redshift number, the more the universe has expanded since that light was emitted, and the further back in time we're looking. Astronomers then combine that redshift with well-established cosmological parameters, including the rate of cosmic expansion and the known proportions of matter, and dark energy in the universe, to calculate exactly how much cosmic time has passed since that light left its source. It's the same basic method used to date the cosmic microwave background itself, just applied to a single distant object instead of the whole sky at once. Faced with black holes that grew far faster than the universe's own speed limit should allow, astronomers have landed on three serious competing explanations. And deciding between them means picking apart exactly how these objects might have cheated the clock. The first possibility is super Eddington growth. The idea that these early black holes somehow found a way to feed faster than the theoretical limit allows, packing on mass through an unusually efficient hyperfeeding mode that manages to choke past the radiation pressure that should be holding ordinary black holes back. Theoretically, this could happen if the accretion disk itself becomes thick and turbulent enough that radiation gets partially trapped and channeled away from the infalling gas instead of pushing straight back against it, letting matter slip past the usual bottleneck. It's an appealing fix because it doesn't require inventing anything new, just an early universe loophole in a rule we already understand. The problem is that recent JWST observations of how these early quasars are actually feeding show remarkably ordinary behavior, not the exotic, boundary-breaking feeding patterns this theory would predict. That's not a decisive rejection, but it's enough to cast real doubt on super Eddington growth being the whole story. The second possibility skips the slow start entirely. Direct collapse black holes, sometimes called heavy seeds, propose that instead of beginning life as the remnant of a single collapsing star, some early black holes formed from the direct collapse of enormous primordial clouds of hydrogen gas. Clouds weighing anywhere from 10,000 to 100,000 solar masses, collapsing straight into a black hole under their own gravity without ever going through a stellar phase at all. That gives the black hole an enormous head start, potentially closing most of the timing gap without needing to break the Eddington limit whatsoever. The catch is that direct collapse requires very specific conditions: enough gas, in the right density, without fragmenting into ordinary star formation first. And it's still an open question how common those exact conditions actually were in the early universe. The third and most exotic possibility reaches back even further than the first stars. Primordial black holes are hypothetical objects that wouldn't have formed from any star or gas cloud at all, but from dense pockets of energy collapsing directly during the extraordinarily frantic first fractions of a second after the Big Bang itself. If black holes like this genuinely existed before the first stars had even formed, they would have had a running head start measured not in millions of years, but from the very beginning of cosmic time, potentially solving the timing problem outright. The catch, and it's a significant one, is that primordial black holes remain entirely hypothetical. None has ever been confirmed to exist. None of these three theories has been confirmed as the definitive answer. It's entirely possible that more than one is happening simultaneously, in different corners of the early universe, and astronomers are still working out how to weigh the evidence for each. Whatever combination of these growth mechanisms turns out to be correct, one thing is now clear from the Euclid and JWST data. These ancient quasars weren't just growing impossibly fast, they were reshaping everything around them while they did it. JWST observations show that these early quasars were considerably more chaotic and violent than the quasars we observe in the more settled modern universe. As they fed, they generated extreme outflows, colossal galactic winds blasting outward from the black hole's immediate surroundings, violently stripping gas away from the host galaxy and heating whatever hydrogen remained, the exact raw material future generations of stars would have needed to form. The consequence of that violence shows up directly in a separate mystery. JWST has been quietly documenting for the past few years an unusual population of galaxies observed just a couple of billion years after the Big Bang that appear old, red, and essentially dead, meaning their star formation had already shut down far earlier than standard models predicted it should. Astronomers call this process quenching, and finding it this early in cosmic history has been genuinely puzzling on its own, independent of the quasar timing problem. These superquasars offer a genuine explanation. By blasting out the star-forming gas in their host galaxies this early and this aggressively, they may have choked off future star formation almost as soon as it began, leaving behind galaxies that look prematurely aged, billions of years before they should have run out of fuel. In other words, the same objects that shouldn't have had time to grow this large also appear to be the direct cause of a completely separate puzzle sitting right next to them in the data. Galaxies that shouldn't have had time to grow old. Two mysteries, potentially explained by the exact same trillion sun monsters. Picture that timeline stacked end to end. A universe barely 670 million years old, already hosting black holes that shouldn't exist yet by the standard clock, already blazing with the light of a trillion suns, already powerful enough to permanently alter the fate of the galaxies growing up around them. Not a quiet, gradual beginning to cosmic history, a violent, accelerated one, with monsters at the center of it far earlier, and far more capable than anyone expected to find this close to the beginning of everything. And this is very likely only the opening chapter. Euclid's Wide Survey, the instrument responsible for this entire haul of 31 quasars, has so far mapped only a fraction of its planned coverage. It's designed to eventually survey roughly a third of the entire sky. Every one of the 31 quasars found so far is now being handed off to JWST and the ALMA ground-based array for detailed, high-resolution follow-up, digging into exactly how each one is feeding and how its surrounding galaxy is responding. And the next specific target astronomers are already chasing is a quasar sitting beyond a redshift of 8, which would push the confirmed edge of this mystery back even further, into the universe's first 630 million years. Here's what stays with me about this one, more than the redshift numbers or the trillion sun luminosities. Every time we build a slightly better instrument and point it a little further back in time, we don't find the quiet, simple, gradually assembling early universe our older models predicted. We keep finding chaos, arriving earlier and moving faster than expected, galaxies more massive than they should be, black holes more grown than they should be, entire regions of the sky rewriting the timeline of cosmic history almost every time we manage to look a little closer. TON 618 did this to our understanding of black hole growth in the nearer, more recent universe. These 31 quasars are doing the exact same thing to the very beginning of everything. That pattern is worth sitting with for a moment, because it says something less about any single object and more about the shape of our own ignorance. Our models of the early universe weren't built on direct observation of that era. They were built by extrapolating backward from what we understood about star formation, black hole growth, and galaxy assembly in the more accessible, nearby universe, and assuming those same processes, running at those same speeds, held true all the way back to the beginning. Discovery after discovery is now showing that assumption was too conservative. The early universe wasn't a slower, gentler version of the one we live in today. In some crucial respects, it may have been more violent, more efficient, and more extreme than anything we currently see around us. It's tempting to treat every one of these findings as a crisis for cosmology. Proof that our models are broken and need to be thrown out entirely. I'd push back on that framing. Nothing about these 31 quasars invalidates the broader picture of the Big Bang, cosmic expansion, or the overall timeline of the universe. What it changes is something narrower and, honestly, more interesting. Exactly how fast the earliest, most extreme structures were capable of forming, in conditions we have never been able to directly observe until an instrument finally became wide and sharp enough to catch them in bulk. And there's a genuine, almost thrilling uncertainty sitting underneath all three competing explanations for how these quasars grew so fast. It's entirely possible none of the three current theories is complete on its own, that light seeds, heavy seeds, and even genuinely primordial black holes were all contributing pieces of the same story in different corners of that first violent chapter of cosmic history. We don't have to know which combination is correct in order to appreciate what's actually happening here. Astronomers are watching the earliest instant of galaxy formation ever directly observed, and the universe, at that moment, is already breaking its own rules. So, somewhere out past 13 billion light years, in a corner of the sky Euclid has only just begun to map in full, there are more of these impossible objects still waiting to be found, each one a fresh data point in an argument about how fast a universe is allowed to grow up. And every time we find another one, the timeline gets a little tighter, and the story of our universe's true beginning gets a little stranger. And every time we find another one, the timeline gets a little tighter, and the story of our universe's true beginning gets a little stranger. Euclid's only mapped a fraction of the sky so far. There's a lot more of this story still to be found, and that's exactly the kind of thing we cover every week on Big Data Vault.